All right, let's start off this video with a manual calculation of the sample standard deviation. Okay? And first thing we need is the formula. Well, the formula for a standard deviation is equal to the square root of the sum of all of our x values minus the mean, sample mean squared, divided by n minus 1. Okay. Now remember, if we had not rooted that, then it would be the variance. So really, this formula here is the variance for the data set, sample variance, and then we take the square root and get the standard deviation. So let's go through and find the actual data. Start over here. It's going to be fairly long. We take the square root of 10 minus, 10 is our first data point, 16 squared. We add to that 12 minus 16 squared. We add to that 14 minus 16 squared. We add to that 15 minus 16 squared. We add to that 17 minus 16 squared. We add to that 18 minus 16 squared. We add to that 18 minus 16 squared. And we add to that 24 minus 16 squared. And again, this is all square root, but we need our denominator, which is going to be n minus 1, and 8 minus 1 is 7. Okay. Now, if you do the calculation, you should get in your numerator 130. And you should get in your denominator, we did it, 7. In fact, let me make this consistent with the formula. It's actually 8, number minus 1, and then it goes to 7. And the square root of that. And if you do that computation, you should get the square root of 18.57. And then if you take the square root of 18.57, you should get 4.31, rounded to the hundredths. Okay. So that is your sample standard deviation, right, equals S. Okay. Of course, if you wanted the variance, then you would not have taken the square root, and you would have 18.57, which would be your sample variance. So you could calculate either one of those. Of course, a cleaned up version is available in the slides for you to compare your answer to. But I wanted to work through it step by step so you can follow. All right, now let's talk about measuring a variation in terms of the variance versus the standard deviation. When we look at different data sets, say here data set A, B, and C, each of these data sets has the exact same mean. Okay, it's 15.5. But they're not the same in terms of their dispersion, variation from the mean. You'll notice, for example, that this data set here, data set B, is not that dispersed from the mean. Most of the data points are very close to the mean, whereas data set C is the opposite. The data points are far from the mean, okay? And data set A is kind of in between. Well, if we were to calculate the variance and the standard deviation, we're going to get the best representation of the dispersion of any of our measures. And the reason is because you'll notice when we do the calculation, regardless of the data set, every data point is included in the calculation. Going back to the previous example, this was our data set. And notice we included every single one of those data points in our computation. 10 varies from 16. 12 varies from 16. 14 varies from 16. All of those were in our numerator. And that's the real benefit of the variance and standard deviation, is you're including all the data. Contrast that with the range. If we were to use the range for, let's say, data set A, we would simply use 21 minus 11. We would use 2 points. We wouldn't even consider all of these in the middle. And that's a problem because it doesn't as accurately reflect the true distribution of that data around its mean. Now, when we calculated the variance, you'll recall that we took each of our data points and found how far they lie from the mean, right? So we took 11 minus 15.5 and then squared it. And we took 12 minus 15.5 and then squared it, and so on and so forth. By squaring those deviations from the mean, we accomplish two things. One, we get rid of negative values. Remember, in any data set, you're going to have some values that are going to create negative deviations. 11 minus 15.5 is a negative number. 12 minus 15.5 is a negative number. And if you don't adjust for this by squaring the data, the deviations from the mean, then any positive numbers that you get are going to offset the negative numbers. For example, in data set B, we have 15 and 16. Let's just take these two data points here. Well, notice they are the exact same distance from the mean of 15.5. 15 lies 0.5 below the mean, so we would get a variation there of negative 0.5, and 16 lies 0.5 above the mean, so we get a positive 0.5 there. Well, if you don't square your deviations from the mean, you're going to get a negative 0.5 here, and you're going to get a positive 0.5 here, and when you add them up, they're going to negate each other. You can see this by going back to our standard deviation formula, right? In my example, using the data point 15 and 16 with a mean of 15.5, you're going to have negative 0.5 in here, and then you're going to have positive 0.5 in here. When you sum them together, you're going to get nothing. They're going to negate each other. But if you take the negative 0.5 and square it, and then add that to the positive 0.5 squared, then you're going to get both values considered. I mean, 0.5 squared is 0.25, and negative 0.5 squared is 0.25. So you would get 0.25 plus 0.25, which is 0.5 in your numerator, accounting for both data points. The other reason that we square our deviations from the mean is because it's going to give more weight to values that are furthest away from the mean. And this has to do with how exponents work. If you take the square of 1, it's 1. But if you take the square of 2, it's 4. Do you see what happened? We went from 1 to 2, but the square went from 1 to 4. So it has this amplification of values further and further away from the mean. We have outliers, values far away from the mean. They're going to be given much more weight than values that are not outliers, that are close to the mean. Previously, we looked at these bell curves to see how the standard deviation and variation are between data sets. Okay, but now we have numerical measurements to do this. For example, if we calculate the standard deviation of data set A, B, and C, it becomes very clear that B has the lowest standard deviation. And that visually makes sense, right? Because most of the data points are close to the mean. Whereas data set C has the greatest standard deviation. And that makes sense because we have values that lie farthest away. We have a lot of outliers from the mean. And then data set A is in between. So visual portrayal or numerical portrayal. This is much more accurate, and that's why we tend to use it with our data sets. And it's obvious that if you're dealing with hundreds, thousands, or tens of thousands of data points, you're not going to be as likely to draw them out in a visual. You're going to use the numbers to compare them. Okay, let's keep going. The coefficient of variation is another measurement that is often used for evaluating dispersion and variation. It measures relative variation. It's always in percentage terms, and it shows us the relative variation in comparison to the mean. It's a very easy calculation once you've got your standard deviation, because what you're going to do is take that standard deviation and divide it by the mean. If you're looking at a population, you would take your standard deviation, sigma, and divide it by your population mean, mu. And you can multiply by 100 in order to get it in percentage terms. But that's not necessary if you're comfortable with the decimal form. And then for the sample coefficient of variation, you would take the sample standard deviation divided by the sample mean. Okay. Let's do an example here. Let's say we have two stocks that we're considering investing in, stock A and stock B. Now, in finance, the standard deviation of stocks, that is how much the price varies on average, is a metric that's used to assess risk. And if you look at stock A and stock B, they both have the same standard deviation in dollar terms, which means each stock on average varies by $5. However, they're not priced the same. The average price last year for stock A was $50, and the average price for stock B was $100. This is where the coefficient of variation is going to help us, because what looks like equally risky stocks in terms of $5 standard deviations are not equally risky when you do the coefficient of variation. So let's do that. For stock A, we calculate the coefficient of variation by taking the standard deviation, $5, divided by the mean, $50, mean price. And we get 10% as our coefficient of variation. Whereas stock B has the standard deviation, same, $5, but the average price is $100. So for stock B, the coefficient of variation is 5%. In other words, on average, stock A has a 10% variation in price, whereas stock B has a 5% variation in price. That makes stock A riskier than stock B. I mean, look, if you're going to buy stock and it says that on average it's going to vary by 10% of its price, whereas stock B is going to, on average, vary by 5% of its price, you would say stock B is safer, right? It's not as volatile, it's not as risky. But the standard deviation alone does not tell us that. It looks like these are equal in terms of their risk. They're not. Okay, next let's talk about frequency distributions. We alluded to these already because I showed you the bell curves. This picture here kind of highlights what a frequency distribution is. Here they've taken various heights and asked people, probably some high school or college athletic group, to get behind the height that represents them. Okay? And you'll notice that you have 5 foot here all the way up to 6'5", and very few people are behind the low height or the high height. These are outliers, right? A lot of people are here in between. And that's what we often see with human characteristics. Not always, but oftentimes you get the extremes having very little people, and then you get somewhere in the middle having a lot of people. That's why we say the bell curve is a good example of the human distribution for things like height or weight or intelligence. For example, if you look at men's height here, the actual data shows that the average height for a man, the median height, is 5'9.5" whereas the median height for a female is 5'4". And then you have the distribution. You have some men that are very short, some men that are very tall, right? But not many. And then you have some women that are very short and some women that are very tall. You'll notice that the distribution is tighter for women. In other words, there's less variation among women in terms of height than there is for men. So that's a good way to start off an understanding of frequency distributions. because it helps us relate what this bell curve really is to the real world that we look at.